So we are starting the first session of CPP. So it's not a session per se because it's only one presentation, but then the next session after the break will be the follow-up on formalized mathematics. And so the first speaker is Sébastien Gouëzel, and he will be presenting a distinguished paper at CPP. Thank you, Sébastien. Please.
A beautiful and sunny city of Rennes. This will be a talk about mathematical formalization. And typically, when you formalize some mathematical notion, often there are differences between the paper version and the formalized version, and this can be for several different reasons. For instance, sometimes it comes from technical limitations of the theorem prover. Sometimes it's because it's more convenient to use some implementation because it will be easier to apply in a formal framework. And there are other reasons, but today I will talk about an example where this difference comes from mathematical reasons. And the reason, in a sense, is that the mathematical literature is a little bit lying, in the sense that you have a very nice notion, it's presented in a very clean way, in a nice setting, and then in other papers, in other settings, it's applied in slightly different situations where the usual definition does not really apply. And so if you formalize a textbook definition, in fact, it prevents you from implementing a lot of applications that you want to implement. And so the message of my talk is maybe if you want to formalize, following textbooks is not enough. So maybe AI, which would try to follow textbook, would get stuck at some point, and mathematicians are still useful. And that's why I'm going to try to convince you today. And this will be about very basic mathematics, about calculus. Calculus is a very important topic. You have a map, and locally you say it's almost a linear map, and then I can use linear algebra. And linear algebra is so powerful that it has a lot of consequences. So first, I want to do higher order calculus, so several derivatives, but I have to start with the usual notion of derivative. I won't do that in one dimension, the baby calculus, because I want to be general, because I want to cover a lot of applications. So I will jump straight to arbitrary dimension, and then in this case, say I have two real norm spaces, and I have a map between these two spaces, and at the point I will say that it's differentiable at this point if it's well approximated by a continuous linear map. So that's very classical definition. You can write it formally. And this linear map that approximates locally your map, it's unique. It's called the derivative of the differential of the map. And it's denoted by, you have a bunch of notations in the literature, say df of x or dxf or f prime of x, and so on. So very good, very nice definition, but in practice, often when you apply it, you're not exactly in this setting, and here is a very basic example of a theorem that you want to be able to write in your formal system. You take a map, and you assume that in the interval 0, infinity is differentiable as 0 with a positive derivative, then start slightly on the right of 0, the value of the function is strictly bigger than the value of the function at 0. And here you see that I'm talking about a function which is differentiable in a closed interval. It doesn't map, it doesn't correspond to the definition above, which was assuming that it was in the whole space or maybe in an open domain. You want to be able to differentiate in closed domains, or maybe sometimes even arbitrary domains. So when you want to formalize the definition of derivative, you will not go for this one, but you will already think about domains, because you have important applications that need this generality. So here is the formal definition of derivatives. We have in Lean, this is a Mathlib talk, but this definition was made by Avigad following the Isabelle implementation, and in MathComp in Rock, there are very similar definitions. So it's a Lean talk, but it would apply to any theorem prover. Take your favorite theorem prover, and the talk would go essentially in the same way. So let's just put some definitions that we will use throughout the talk. I define some predicates saying that a function has a derivative within a set at a point, where within the set means that you will just look at you want to have this linear approximation, but just along the set. And outside of the set, the behavior could be arbitrary. And then you say that the function is differentiable within this set if there is some derivative within this set. And then sometimes it's handy to be able to put your hand on some derivative. So I also introduce a definition f deriv within for some derivative of the function within the set at the point. And in this definition, it's convenient not to assume that the function is differentiable. Just because you don't want to provide the differentiability proof every time you call this function. So just say that if your function is not differentiable at this point, the derivative is 0. It's arbitrary, it's a junk choice. It's not really important. It's just a technical choice where it deviates a little bit from the usual mathematical practice. It's a convenient choice for the formalization. And these are definitions in the set, but I will also need definition on the whole space, where you just remove the within in all the statements. And then here is a small warning that in the generality of domains, derivatives are not unique in general, which is a little bit a pain, but that's life. For instance, if you're in R2 and you take the horizontal line, and then if you're asking if a function is differentiable at the point of the horizontal line, it will only look at the values of the function along the horizontal line, and so the vertical direction, there is no constraint. And so if a derivative is working and then you change it in the vertical direction, the new derivative will still work. So you don't have uniqueness, which means that you have to be careful. For instance, even if you have two functions which are differentiable within a set, the specific choice f deriv within of the derivative within this set of the sum is maybe not the sum of the f deriv within because of the lack of uniqueness, and you have applied choice at some point to choose this derivative. That's life. Some domains are good, some domains are not good. And I don't want in the definition to put the assumption that the domain is good, because again, it would be an additional burden to put on the user of the theory. So let's try to avoid as many assumptions as possible in the definitions and only put the assumptions in the statements of the theorems. Okay, so that was for one derivative. And now I want to do higher order calculus, because approximating a function by a linear map is often not enough. You need to approximate it by polynomials, so at a higher order. And the textbook definition is the following one. You take two real normed spaces and map between the spaces. It's C0 if it's continuous. It's C1 if it's differentiable everywhere and the derivative is continuous. And it's Cn if it's differentiable and it's derivative. It's derivative, so it's a map from the space to a space of linear map. And so it's a map between, again, two real normed spaces. So we will say that the function is Cn if it's differentiable and the derivative is Cn minus 1. And then you get the definition by induction like that. And you'll see infinity if you're Cn for every integer number, natural number n. So and that's the paper definition. And in books, there are, well, not sheets, but abuse of notations. With this definition, the second derivative, it's a map to a linear space of maps from the space to the space of linear maps. So it's a little bit awkward to work with, and in practice with the anchoring step, you realize that this space of linear maps into linear maps is the same as continuous bilinear maps. And so people only work with continuous bilinear maps. And in the same way, the nth derivative is, by anchoring, it's canonically identified with an n continuous n multilinear map. And in practice, that's what people do in books. And in practice, when you formalize, it's a little bit of pain because you have to pay attention to these anchoring steps, but that's that's life, and you think that's more honest than what you will find in books. And I will put that under the rug because it's not especially interesting. It's just something you have to do. Okay, this definition is well and good, but it has several limitations that makes it not so suitable for if you want to build a library where you can formalize a lot of mathematics. For instance, I only gave it about the real on the real numbers, but you also need it for complex numbers and even for more exotic fields like QP. And if you don't know what QP is, it's not a problem for this talk. Just know that it's something a little bit more exotic, but not so exotic. There are more exotic fields, normal field like that, and this one. Second limitation in my eyes, it's only written on the whole space. But as I said, even on for first derivative, we need to do it in domains. And if you want to do manifold with boundaries, things that are really important in mathematics, for instance, in Perelman's solution to the Poincaré problem, you have manifold with boundaries everywhere. So you want manifold with boundaries, and for that you need smooth functions in domains. So you need to put domains in the definition. And then argument of authority, Bourbaki tells you that it's not the right thing to do because you also have to think about analytic manifolds. And so you really want to look at Cn for n, which is either a natural number or infinity, or omega, meaning analytic functions. And Bourbaki tells you should do that, so probably they have a good reason, and they have a good reason, and I won't really have time to talk about it unless I'm really quick. So if I want a suitable definition of Cn functions in Mathlib, I should solve these three difficulties simultaneously. So let me try to be naive and introduce a definition following the textbook definition, but in domains, because we want domains. So I could define inductively the nth iterated derivative as a derivative of the n-1th iterated derivative plus a occurring step. And I could say that f is Cn on a domain if this nth iterated derivative is well-defined and continuous up to stage n. And I told you that in a domain, the derivative is not unique, which means that it can be very bad. There is choice in the definition, so it could be extremely bad, even on the horizontal line and the function L of xy equal to x. It might not be C1 because the derivative might not be continuous, because I told you it was arbitrary in the vertical direction. So your choice could take you 1 along rational points and 0 at irrational points. Choice is maybe stupid. You don't know anything about it. So with this definition, it's bad. So you should avoid this f-derivative within which has an arbitrary choice baked in. And you should rather talk about the existence of a nice sequence of iterated derivatives. And that's my second try. I could say that a function f is Cn on some domain S if on this domain I can find a sequence of m multilinear maps, Pm, where P0 would be your original function and Pm plus 1 would be a derivative of Pm, and they should all be continuous up to stage n. And that's a natural definition if you want to avoid the issue with choice before. And this definition doesn't work as well as one could think. And the reason is that with this definition, if a function is Cn, say for all natural number n, it's not obvious that it would be C infinity. And the reason is that these Pm's that you choose for some n, they wouldn't have to coincide with the one for n plus 1 because of the lack of uniqueness. And maybe when you increase the n, you have to make some weirder and weirder choices. You have no guarantee of compatibility, and maybe you could not glue them together to form a Taylor series up to infinity. Of course, if you have uniqueness of the derivative, then you're fine. If you can glue them together using partition of unity, say if you're on the reals, you're fine. In most situations you can think of, you're fine. But it's not obvious that you're always fine on weird fields where you don't have on set where you don't have uniqueness and where you don't have partitions of unity. You could not glue them together. You're just stuck. So you're stuck. You have a locality problem in time. I say for the different ends, maybe you could not glue them together. But also in space, if your function is Cn around every point in S, maybe the PMs coming from these different points would not coincide and so could not be glued together. So this locality problem, you have to solve it, and you can try to prove a theorem saying that you can always glue them together, but I don't know how to do that, or you can change the definition. And that's what I did. And here is my third try. I will localize the definition. I will forcing a local definition. I will say that at a point x, the function is locally Cn around this point. If for any natural number n prime, I can find a sequence of derivatives up to this n prime. And then I will say that the function is Cn on my space on the set S. If locally around each point, you can find such a sequence of derivatives. That's essentially the previous definition, but localized by force. And in this way, the definition is nice. It has to be local. And for Cn and natural number or infinity, this works fine. And then I have to say what analytic functions mean. And analytic functions mean that locally you have a power series. And so I could say that C omega is just analytic, and it creates a function, a problem that an analytic function is in general not C1, which, okay, what is it saying? It doesn't have to be C1 if the target space is not complete. That's crazy, but if you're analytic at a point, target space is not complete, you move a little bit your point, and the new power series at that point doesn't have to converge, and so maybe your function at the other point is not analytic, and maybe it's not even differentiable, and you can build up stupid examples. So that's a fact of life, and that's bad, because you want a C omega functions to be Cn. You want a monotonicity of this class in terms of n. So let's tweak the definition in a stupid way and say that a function is C omega if it's analytic, but also it has a sequence of derivatives which are all analytic. Okay, and then C omega will imply Cn. So that's really just stupid tweaks to the definition to make sure that it applies in all reasonable situations. And so here is the formal definition we have in Mathlib, which is a little bit unwieldy, and I will not enter the details of the formalization because it's exactly just what I explained. Well, just what I explained in formal terms, where you distinguish between the case of a natural number of infinity and omega, and you just want to have locally formal Taylor expansions with a nice behavior. So that's it. And once you have this local definition of Cn functions, so we pick condiff within at, which is already a mouthful. Initially, we had times condiff within at because it's several times continuously differentiable. It was too long, and we just dropped the times. So the name is a little bit silly, but we couldn't come up with a better name, and then we're used to it. And then once you have it at a point, you define it on a set, on the whole space, and so on and so on. Okay, and in the 3 minutes left, I'll talk about an application. Because in fact, we didn't come up straight away with the definition you've seen. It was prompted by more advanced formalization that made me realize that, in fact, the definition we had initially was bad. So I wanted to formalize Lie groups, which is a more advanced notion, but which really need calculus. And so what is a Lie group? First, I want to define the Lie bracket of two vector fields. You have a vector space, you have two vector fields on them, and then you define a Lie bracket, which is a quantity that measures how much the flows of the two vector fields don't commute. And there is a formula, which is not interesting, what is interesting is that this notion of Lie bracket, it's invariant under diffeomorphisms. If you have a local diffeomorphism and you pull back two vector fields, and then the Lie bracket of the pulled back vector fields is the pullback of the Lie bracket, which means that it's a good definition because it's canonical in a sense. And this means that if you have manifolds which are like the sphere or whatever, smooth spaces which locally look like vector spaces, but which are not vector spaces, you can pull back this definition of Lie bracket to manifolds, because any notion which is invariant under diffeomorphisms can be pulled back to manifolds. And so you can define the Lie bracket of vector fields on manifolds. Warning here, I put some condition, has symmetric second derivative, which is needed here. And so once you have pulled back this notion of Lie bracket in manifold, you can define the Lie algebra structure on the Lie group. A Lie group is a manifold where you have a multiplication and an inverse that are smooth. And once you have that, you can put a very nice algebraic structure on the tangent space to your Lie group at the identity the following way. You take two vectors, you push them everywhere in the group by multiplication, you get two vector fields, you take their Lie bracket, you look at the value of the Lie bracket at the identity, and it's an extremely well-behaved algebraic structure which satisfies a lot of axioms. It's a Lie algebra. And that's it. But to define this structure, you need this invariance of Lie bracket under common. Okay, under diffeos. Okay. Okay. And so you need symmetric second derivatives, and 30 seconds, I promise. You need this symmetry, and this symmetry is true most of the time. It's true over, well, most of the time you can think of over R or C, it's always true. And over any field, it's true for analytic maps. And over QP, the field I mentioned before, it's not always true. There are infinity maps for which the second derivative is not symmetric, and you can just write down stupid explicit examples. So if you want to do Lie groups over all fields in a nice way, over R or C, it can be for C3 manifolds, because you need the symmetry of the second derivatives. So over R or C, it's okay for C2 or C3 maps. But if you're over a different field, you need analytic manifolds. So if you want to do Lie groups in a unified way over all fields, you need a class of Cn functions which include analytic functions, because you want to be able to talk about Lie groups on over QP. And that's why Bourbaki did it with Cn or C infinity or C omega, precisely to be able to treat manifolds in a unified way. And they were right to do so. And once you have realized that, you can, okay, here is the fact that in Mathlib, the Lie algebra of a Lie group, well, the tangent space and the identity of a Lie group is a Lie algebra. It has some assumption that it's a smooth. Okay, I get it. It's a Lie group, and the smoothness will have to be depend on the field. If the field is R or C, it can be 3. If the field is not R or C, you need an analytic manifold. And so the takeaway message is that there are two ways to get good definitions. Either you think of everything at the start, and you write it down, and you're perfect. Or you write down a definition, you develop a lot of theory, and then you get a more advanced example, and you realize that your initial definition is not good enough to cover that, and you refactor everything. And that's the way it works in the real life. And that's the way it happened for this definition of Cn maps in Mathlib, where at the beginning, we didn't integrate analytic maps. And then we were beaten pretty hard when we realized we had to change everything. And then, well, we did change everything. Thank you very much.
We have time for one question before the coffee break. Mic from the back.
In software design, we know this problem of refactoring all the time, and we try to design for it. Is there a possibility to do this in this approach as well?
Definitely. The idea is once you have your definition, you try to build up some API where you list all the useful properties that you will use. And then once you've built up this basic API, do not ever unfold the definition. And then when you see that you have to extend or change your definition, you just have to fix the API. And if your API was well designed, it will still work with the new definition. And then all the theorems that were written just using the API, you don't need to fix them. And that's what happened here. In fact, the refactor was, okay, it was bad. But it was not that bad.
Thanks, Sébastien, again.